Oh, hi. Didn't see you there. If you're interested in engineering, this video will be right for you. Today we're going to take a look at Bernoulli's equation. You're going to want to be comfortable with chem and physics, or at least unit conversions and equations. So the idea with this experiment is, if you have an L-shaped tube, you can submerge this in water and calculate the velocity of the water inside. So to do this, you just need to get some tape and some PVC pipe that you buy at Home Depot. I got it for less than $5. You just kind of put it together and you have a velocity measuring device. What are we waiting for? So the idea with this experiment is, if you submerge this in a river, the water will flow through, go through the pipe, and reach a point of equilibrium. You can then measure the height, plug it into an equation, and calculate the velocity of the river. The equation is square root of 2 times gh, where g is a gravitational constant, and h is your height. Since I don't have a river, I just use this to calculate the velocity of the water in my faucet. Okay, so the next part of the experiment is where the math takes place. You're going to want to be comfortable with unit conversions. A quick tip on learning unit conversions is, if you think it's difficult at first, just keep chugging through it, keep doing your homework, and eventually it'll be easy to you. Just think about a talent or a hobby you have that used to be difficult, but now it's just as easy. Okay, so the height that I measured was 10.5 inches, which I converted to meters. I got 0.26 meters. Plug that into the equation and simplify, and we get 2.28 meters per second. Cool, so now we're done with the experiment, and now we have the velocity of the water, and we're just going to test how accurate we are. So if we think about dimensions, we can sort of write an equation saying that velocity times area is equal to your volumetric flow rate. The concept of volumetric flow rate is simply how much water you can fill in a bucket, for instance, in a certain amount of time. So I measured the area of the faucet. I got about 1/4 of an inch, plug it in, get the area, pi r squared, and multiply to the equation, and that gives us the volumetric flow rate of the faucet. So now to really test if this is actually accurate, I measured the volume of a bucket and calculated how long it would take to fill that bucket. So for the volume of the bucket, the diameter I measured was 10.75 inches. Bear with the math. I converted that to the radius, or you just multiply into the equation, and then I multiplied it by the height, and I got the volume of the bucket as 0.0148 meters cubed. So then I divided the volumetric flow rate by the volume to get approximately 51 seconds. So that's how long it should take to fill the bucket, but it ended up being a little bit longer than that. Okay, at this point, you're gonna wanna have taken a physics class or be pretty comfortable with equations, because we're gonna show the derivation using Bernoulli's equation, which is an energy balance for fluids. So this states that delta P, the change in pressure over the density, plus the change in kinetic energy, plus the change in potential energy is equal to 0. Basically, fluids are in equilibrium. So our system is the L-shaped pipe inside the river flows, water goes through the pipe, goes to the top, and at this point it reaches equilibrium, and the water here is not moving. So in other words, V final here is 0. Cool. So that allows us to simplify this equation, because if we expand it, we can cancel out the V final term. Also, we're going to let our H be 0 at this point, so all we have to do is find this H here. We continue with this calculation, delta P over rho plus. Now we've got rid of the final velocity, so now we have negative U initial squared over 2 plus G, and we got rid of the H naught, so we have H final equals 0. Now, the key to this equation is that the system is in equilibrium. So the energy at point 1 must be equal to the energy at other places, especially here since it's at equilibrium. So that's our system that we're analyzing. Bear with me. What that means is, the idea is we can cancel out pressure. So we're going to see what happens. We're going to move it to the other side. Move that over, negative U initial squared is equal to negative GH, negative cancels out, over 2. So we're going to multiply the 2 over here, 2GH, and boom, we got them. Boom, 2GH. It's the same equation I use. So 2 is a constant, G is a gravitational constant, 9.8 meters per second squared. That comes from potential energy. All you have to do is find this H from the height of the water in your tube, and that's your equation. If you made it this far, congratulations. I'm actually pretty surprised. Although there were some errors in my results, I was able to calculate using an equation, which is something that engineers do every day. One of the biggest assumptions that I made was that the fact that the pressure terms were equal. This is because of the fact that the states were both in equilibrium. But technically there are some differences that I believe led to my error. If you happen to have done this experiment, please let me know what you think. Give me your feedback in the comments. I guess I'll leave my email. If you enjoyed this type of video, I hope to make more engineering projects in the future, so you can subscribe or like my videos.